Okay, and right. So I want to go through each slide for chapter 8 because some of the contents are not very relevant now. And if it's not that relevant, it won't be included in exam. So if you are interested in all this background knowledge, I will got the YouTube video you can watch that is done slide by slide. So for so in class, I will go through some very important knowledge point. Question there. Okay, you can see. Okay, so chapter 8, we had this a list of SR GK flip-flop. They are very interesting concept, and we used to use them to build a sequential circuit. Now, what we have on the FPGA is only one type of flip-flop, that is D flip-flop. And that is the only real thing that we can get from the hardware. So we build everything else based on this D flip-flop. That's why we will spend some time to explain what it is and how to use it to build sequential circuit. So this is the definition for flip-flop. And so before this, there is another definition for latch, which we don't recommend. We are not encouraged to use latch in sequential design because latch is not related to any clock. That's why it's a latch. It's level sensitive. So anything that has a relation to the clock, system clock, the one and only system clock, we call it a flip-flop. So it's got an input for a clock. So it is a gated latch with a clock input. So again, latch is very simple. It passes the input value to the output. Latch the input value to the output. Whenever input change value 0, 1, 1, 0, output will follow after a very small delta delay. Okay, so after a very small delta delay, we will see the output change following the input. That is the latch. So flip-flop is similar to latch, but with a clock. So this latching, this recording of the catch of the input and pass the input to the output. This action will only occur on the rising edge or the falling edge of a clock. So that's the difference between these two, latch versus flip-flop. So flip-flop is edge sensitive and latch is level sensitive. So definition of clock. Clock has a positive edge when that 0 is so clock signal. When we talk about a clock signal, normally we have a 50% duty cycle. Okay, so clock signal. This is the most important signal in our system, in synchronous system. So you can never get away from this signal and design a synchronous circuit. So for this clock, it has a 50% duty cycle. So, and it has a rising edge, and falling edge. With your with the design right now, if you use with the in the lab, you can either use a rising edge or you can use a falling edge. Try not to use both because there is no need for it right now. I have used both for the reason of increase data throughput. The system, the transmitter and receiver data, I want it to be faster. That's why when I can use both edge, but it can generate tighter timing requirement for your system. Timing requirement. This is what we can, if we have time, we can talk about it later. So the timing requirement for your system is referred to the frequency, the maximum frequency that you can run with your design. So it is defined not by you, it is defined by the client or by a customer who wants a faster system. Then this specification is given to us as the engineer. So we decide how to design a system to meet that timing requirement. And then you can figure out how to do that in many different ways. The simplest way is to use a better FPGA, faster FPGA. But normally that will cost more. This is not everybody like to see. So to reduce the cost of the design, you probably want to figure out how to implement your design in a different way. For example, use both rising edge and a falling edge of the clock. But that means mapping the synthesis and implementation will be harder for your design. Okay, so I will stop there if this is not that relevant to software. So let's come back to the clock. So the positive edge is a rising edge, the negative edge is a falling edge. So this is the definition. And the symbol of the clock on the circuit is a triangle. So that is the input of the D flip-flop. So rising edge, falling edge of the clock. And this is the symbol for the D flip-flop. Okay, so we have this input for clock, and we have the D input and two output, Q and Q naught. So basically they are the same thing, but they provide us with the truth form and the complement form. So you can select select a suitable one for your circuit. Either it's active high or active low. You have both here. You don't have to have an additional inverter. So this covers both. So this is the general form of D flip-flop. D flip-flop is the smallest memory element on the FPGA. So 1 bit of D flip-flop can store 1 bit. So 0 or 1, the value. It can store the value. How to store the value? It's because every time there is a rising edge of the clock. So D is the input, and let's say this is a value, the data value. Okay, so let's say this is 0 and 1 and 1 and 0. So D is the input. On the rising edge of the clock, this value will be stored in the D flip-flop. So the input value will be registered into the D flip-flop. That's why we also call the D flip-flop a register. RTL level design, if you have heard about it, is related to FPGA. It's a register transfer level. It's related to this fundamental element within the FPGA, that is the D flip-flop, which is also called the register. It's a very basic, smallest memory element that we can use. We call it the FPGA logic resource. So when the data input is 1, the output, the clock is on the rising edge. This means the output here will get 1. So that is Q. Q is the output. And Q naught will get inverted of Q. It will be 0. Okay, so this is how the D flip-flop works. It only works on the rising edge or falling edge of the clock. So after this, it's just blind. It won't even look at the input. So the input so between two clock rising edge, the whole D flip-flop will just completely ignore the input. So between these two, D input can go crazy. It can be 0, 1, 0, 1, change many times. So basically it would be like up and down many times. This could be noisy. So noise signal in our circuit. It could go up and down as a noise signal. We often have this like a switch. You have some slides there for debouncing circuit. That is very noisy, but it won't affect the output for the D flip-flop because the D flip-flop won't check the change of the input until the next rising edge of the clock. As long as D input is stable before the next rising edge of the clock, we call it a setup time. So a small time period before the next rising edge, it is stable. So at the next rising edge of the clock, it will register, it will take in the input value of D. Now it's 1, so it will be 1. It will register that and then store it in the D flip-flop. That means on the output of the D flip-flop, it will be this signal. Yes, question. There is very small propagation delay for the D flip-flop, but it would be irrelevant because we don't. So the propagation delay will be a lot smaller than the clock period, and that is the condition for this to work. So that's very good. You mentioning the propagation delay. For D flip-flop is not very relevant because D flip-flop is edge sensitive. It only works on the rising edge of the clock. And that is so purposefully designed precisely for the propagation delay introduced by the logic, which is an AND gate, multiplexer, demultiplexer, encoder, decoder. Those are logic. So many gate, AND gate, OR gate, XOR gate. Those gate, if you have many of them in the design for very complex logic, then that will introduce a lot propagation delay. That will affect the speed. Then we have to make sure that all those propagation delay combined together is smaller than 1 clock cycle. So it should be smaller than 1 clock cycle. Otherwise, what would happen? That means so the input comes in, after all this combinational logic, we expect to see the output at the next rising edge of the clock. But at that time, the output is not stable. It's still passing all this gate and trying to work out the final logic output. So that is called the worst negative slack in the design, and that is something that you can see in the Xilinx design report. So even if you just have simple AND gate, NOR gate, this type of simple logic defined with your design. After you implement it, you will see the report that gives you this worst negative slack when you introduce the clock signal. So it worked out against the clock period time. Right. So this is how the D flip-flop work. And you will see this lot. It looks so complicated in disguise. It's very simple, actually. So this is just don't get scared by this table. It's indeed a very simple concept. So if you try to read through it, basically it means this thing only works on the rising edge of the clock. So when it's on the rising edge of the clock, the output will equal the input. So basically T+1 means next clock cycle. T is when, so this first clock cycle, this value get latched, or not latched, get registered into the, get remembered by the D flip-flop. And the next rising edge of the clock, that we will see it on the output of the D flip-flop. So the other lines here, when clock is 0, when clock is 1, when the clock is on the falling edge, D is don't care. That means the D flip-flop will retain the memory, will keep what it catch at the first rising edge of the clock, and will return that value, will memorize that value. That's why it's a memory. So all these 3 lines here only means don't care, won't see whatever D is changing, it won't get registered into the D flip-flop. So basically, how does the D flip-flop work? It only works on the rising edge of the clock. When it sees the rising edge of the clock, it will store the value on the input into the D flip-flop, and then pass that value to the output. At any other time, when clock is high, clock is low, or clock is the falling edge, it does nothing. It does nothing. Yeah.
If Q is an active pole, then we would care about the falling.
Not D, clock. If clock is active low, another good question here. So if do we have now we don't have the sample, but for that one, you have the triangle of a clock. If you have the bubble on there, so on the input of the clock, then that means we are using the falling edge of the clock here. If you have a bubble on the clock, not on D. So although, yeah, we can argue that D can have an inverter in front of it to make it, but there's it's not. So it's not normally what we do here, because it's a D flip-flop. It's the fundamental element we use to build our logic. And it's only related, so the active high, active low is only related to our logic input and output. Right, okay, so positive edge triggered D flip-flop. So we'll jump directly to the edge detector. So this design is interesting, but is not a common practice now. So, but it's interesting to know how the edge detector using the NOT gate here, inverter here. So we have the input X. How to so let's say we want to detect the rising edge of the clock. How to do this? This is a very simple way, interesting way of doing it. So basically we have the input clock and we put a inverter there. And then we add these two together. And that goes back to the previous question about the propagation delay. the delta delay, propagation delay. So we're talking about that, the small delay of not the AND gate, the inverter. So the inverter here has a small propagation delay. That means when the input change, after a small propagation delay, the output will change, right? The output will change. So the input X looks like this. So low and then high. And then the inverted one, so the output of the NOT gate, the inverter, the output of the inverter is X naught, will be the flipped version of X. The output of this will have a very small delay. Is this easy to understand here? There will be a very small delay here for the output to change from 1 to 0. And to add these two together, we get Y output. So when they are both high, the AND gate output would be high. So that small pulse or spike here is the output signal, indicate that we detect a rising edge of the signal. Okay, so this is an interesting circuit, but it's not very practical now in our digital circuit design. So, but it's a interesting idea. Okay, check. So I will discuss the latch, the D flip-flop. So what we can see, so as I said, JK flip-flop, if you are interested, you can have a look at so how it is defined. What we are going to focus is on the D flip-flop only. Still have a few minutes to just cover this master reset. So again, this is a GK flip-flop. Master reset is normally is asynchronous. But if you read Xilinx technical report, it will always recommend us to use a synchronous reset. So we will, in the future, we will look at how this is implemented by VHDL code. Synchronous and asynchronous. So this is a concept I want to just have a quick talk about. So synchronous input of a flip-flop only affect the output on the active clock edge. Synchronous, asynchronous input of a flip-flop change the output immediately. So asynchronous, we know that D works only based on the rising edge or falling edge of the clock. So this input is synchronous. So anything if it's only checked with the clock is synchronous. Synchronous is so it's related to clock. If it's not related to clock, it is level sensitive, then it is asynchronous. So means it's not synchronous. It works on its own. Yeah, it's whenever it can happen anytime, it will affect the output. So we have asynchronous reset, asynchronous clear. So that's asynchronous input to the D flip-flop. Yeah, so that's answer your question. Okay, good. So this is the last thing I want to mention. So you can see now that is active low, asynchronous reset, asynchronous clear. So so sometimes we connect these together if they are available and make a master reset out of it. So everything, the reset or the clear of everything, every D flip-flop are connected together. So they are the mastered reset.